In this lesson, we will look at some popular finite elements for the Stokes problem, and we will prove the Inf-sup stability of some of the simple ones. Let's recall the general theory of saddle point problems and their discretization by finite elements. So here we have the general form of saddle point problems. And so we have the spaces V and Q. In general, they are reflexive Banach spaces. And we consider subspaces V hat and Q hat. Then, for the well-posedness of the discrete problem and quasi-optimality of the Galerkin solution, we need two conditions. First, we need to have this operator called A hat 0 invertible. A hat 0 is basically the operator A corresponding to this bilinear form restricted to the kernel of the discrete operator B hat. B hat is the restriction of the operator B defined through this bilinear form B, basically restricted to the discrete spaces V hat and Q hat. And the second condition is the discrete Inf-sup condition for the bilinear form B, and this is, we know that it's equivalent to saying that the transpose of the discrete operator B hat is bounded below. And we know we introduced last time one way to show discrete Inf-sup condition, that is through the so-called Fortuyn operator. Fortuyn operator is a linear bounded operator that sends V to the discrete space V hat that has this property. Okay, now let's specialize this to the setting of the Stokes problem. Now for the Stokes problem, we have the V, that's called the velocity space, that's H10. We are taking the Dirichlet boundary condition. H10 vector valued, and the so-called pressure space is the L2 functions with mean 0. That's the space Q. And in this case, we have the operator A is minus Laplacian acting on vector fields, and B is minus divergence, and B prime is the gradient operator. And the corresponding bilinear forms are here. For A, here U and V are vector fields, so the gradient, this would be, or the Jacobian would be a matrix, so that's why we wrote the inner product in this way. And the bilinear form B, that corresponds to that operator here, is simply that, the scalar field multiplied by the divergence of the vector field. Now, so from the two conditions that we mentioned, the first condition is trivially true because this operator A, or this bilinear form A, is coercive on H10, or strictly coercive in H10. So this means that it is strictly coercive in any of its subspaces, in particular in the discrete subspace. So there's no problem with invertibility of A0 hat. That means that we only need to focus on the Inf-sup condition for the bilinear form B. And if we want to use the Fortuyn operator to show that, now we need to construct this operator, V to V hat, which is uniformly bounded. Uniform meaning that it should not depend on the mesh size parameter that should come in here. That has this property. And you can also look at it in this way. So you bring everything into one side, then you see that Q integrated against the divergence of V minus pi V is equal to 0 for all Q from Q hat. So basically what it is saying is that divergence of V minus pi V is L2 orthogonal to the space Q hat. So we want to construct such an operator. Now, there are many finite elements designed for Stokes equations. And the first one, the very simple one, this will turn out to not work actually. But the first one that comes to mind is this element, the so-called P1, P0 element. In this case, our v hat, the discrete space for the velocity, is just globally continuous piecewise affine vector fields with respect to some triangulation P. Of course, we have zero boundary condition. So it's just the usual finite element, except that it's vector valued. It's Lagrange finite element with vector values. And the pressure space in this case is now discontinuous piecewise constants with mean zero. So that means that the degrees of freedom will be over the triangles here. And for the velocity space, the degrees of freedom will be over the vertices of the triangles. So we want to use this opportunity to also discuss some general points that will be actually valid not only for this finite element, but will be valid in general. Remember that b hat, the discrete operator or matrix, is defined in this way. And you can see that if you bring everything again into one side, you can see that that just means that b hat v is simply b applied to v, and then you project it onto the q hat. Now we are assuming now the q hat or q is a Hilbert space. So in this case, this will be an orthogonal projector. In particular, for the Stokes problem, we have L2. So q is a Hilbert space. So we're going to have here L2 orthogonal projector. This would be discrete divergence in our case. That would be simply continuous divergence followed by the L2 orthogonal projector onto the pressure space. Now in this case, this particular case, P1, P0, if you take divergence of P1 vector field, continuous piecewise affine vector field, you're going to get some piecewise constant function. That means the application of the L2 orthogonal projector onto q hat will be trivial because you already have something in q hat. That means the discrete divergence is actually equal to the exact divergence. In particular, remember in the Stokes problem, the second equation is b hat u equal to 0, and because b hat is actually divergence itself, the divergence free constraint will be exactly preserved in this case, which is a good property. And this is true whenever this property is true. Because we are approximating the velocity by piecewise affine functions, and the natural space for velocity is h1, the approximation order is OH. And for the pressure space, we are using piecewise constants, but the natural space for pressure is L2. So again, the approximation order is OH. So these two orders are consistent, meaning that we are not wasting any approximation power here. But okay, now we want to show that this element is actually unstable. For stability, what we need bounded below property of b hat transpose, and that will imply that b hat itself is surjective. So now let's look at the degrees of freedom for the velocity space and pressure space. So let's look at this particular triangulation as an example. We have zero boundary condition for the velocity. That means there is no degrees of freedom on the boundary, and the only degrees of freedom are on the interior vertices. So in this case, we have three interior vertices, and on each vertex we will have 2 degrees of freedom. So basically it means that there is going to be one finite element space for the x component of the vector field, and another finite element space for the y component of the velocity vector field. And the pressure, you're going to have 1 degree of freedom per element. Okay, so you can immediately see that there are lots of degrees of freedom for pressure and very few degrees of freedom for velocity. And if you remember what this b hat is doing, b hat is actually sending v hat to q hat, and we see that q hat has lots of degrees of freedom, but v hat has very few. So that means, at least for example, for this mesh, this particular mesh, b hat is not going to be surjective. So it is Inf-sup unstable. To prove that it is unstable on a general mesh, we are actually in this lesson we are focusing on only two-dimensional case. So in two dimensions, we can do this counting. So you count the sum of the interior angles on each vertex, and you sum all those angles. So if you do that, let's say V is the number of interior vertices, then we will have on each vertex we're going to have 2 pi angle. So 2 pi times V will be the sum of all those angles. We can also count that angle by using the faces or the number of triangles. So on each triangle we will get 180 or pi. So that means the total angle will be strictly smaller than pi times the number of triangles, and that gives us 2v is smaller than v. Now the dimension of v hat is equal to actually 2v, and dimension of q hat is equal to f, because it's the number of triangles. You see that this condition tells you we can't have surjectivity because the pressure space is too big. So it's not surjective, and P1, P0 element is unstable for the Stokes problem. You can also express it in terms of the B hat transpose. So B hat transpose enters in the first equation. So if you remember, we get equation like this: A hat U plus or minus B hat transpose P equal to some discretized version of F. So because B hat transpose is not injective, that would mean that pressure is not going to be now unique. So these pressure modes are called spurious pressure modes, which are not real pressures. Okay, so this element doesn't work, and the reason was that the velocity space was too small. So you have too few degrees of freedom for the velocity. So the next natural idea is just to increase or enlarge the velocity space, and take, instead of linear finite elements, we take quadratic finite elements for the velocity, and keep the piecewise constants for the pressure. So right away we can notice that, just to discuss some general points, because we are using the second order quadratic elements for the velocity, potentially we should have second order convergence for the velocity. But because we're using piecewise constants for pressure, we're going to get first order convergence for the pressure, and the minimum of these two is first order. So in other words, this P0 element that is used for the pressure, it's going to actually pollute the approximation of velocity, and this will not be realized. Both will actually be first order in general. So we're going to get first order. So that means we are not really utilizing the full power of P2 element here. So in some sense, it means it's not optimal. Now, the second point is that divergence of the velocity space is not included in pressure space, because there are quadratic vector fields, and there is going to be in general some linear component in the divergence of that vector field. So that means discrete divergence constraint. The divergence constraint is satisfied only on average. So I think we should not say it's discrete divergence constraint. The discrete divergence constraint is here. This is actually satisfied. So because pressure space is piecewise constants, the discrete divergence constraint really is exactly this. So it tells you that the average of the divergence over each element is 0. So that's what I mean by the divergence constraint is satisfied only on average. And we can do integration by parts to imply that this boundary integral, or you can see that this is velocity, and here we have normal, unit normal on the boundary. So you can see that this is total flux over the boundary of the triangle, which should be 0. This is called local mass conservation. So basically it says that what goes in must go out. Even though the divergence constraint is not satisfied pointwise or exactly, it is only satisfied on average, we actually have local mass conservation. This, you can see that this is always true whenever the pressure space contains piecewise constants. Let's try to construct a Fortuyn operator. Again, so we write here what we need to construct. The Fortuyn operator is a uniformly bounded operator sending v to v hat. So this would be now our P2, of course, and it should satisfy this equality. So let's put everything into one side, and let's write that condition in this way. So Q integrated against the divergence of v minus pi v, and we also split the integral over the triangles. Then we do integration by parts. So when you do integration by parts, there is going to be a gradient of Q, but Q is piecewise constant. So on each triangle, the gradient of Q is 0. So we will only get boundary terms over here. This boundary term is Q multiplied by the normal component of v minus pi v. So you can see that this normal component of the difference between v and its projection should be 0 over all the edges. So that would ensure that pi is a Fortuyn operator. So in particular, a sufficient condition would be, instead of ensuring that a normal component of this difference 0, we can actually ensure that that difference itself, the whole difference, is actually 0 over each edge. So that will ensure that we have a Fortuyn operator. So let's look at this picture here. We have a quadratic finite element with vector unknowns. So we have 2 unknowns here and 2 unknowns here, and so on. So if you look at one edge, one particular edge, so you're going to have one bubble function on the edge and 2 quadratic functions. You can also take this linear shape function, and we're calling the edge length h. This BE is the edge bubble function that corresponding to this edge, which would be supported in the 2 triangles which include this E as their edges. So we're going to define this pi v as linear combination of those edge bubble functions, where this lambda e, they should be now actually vector valued, because v is a vector. To simplify things, we can think of v as a scalar because everything works in the same way. So we are defining pi v as linear combination of those bubble functions, where the coefficients are defined by this relation. You see that when you integrate this over an edge E, this sum will disappear, and it will pick up only one edge, and integrating, because lambda is constant, it will be just integrating over here, and that we want to be the integral over v. So that this condition is just the condition over here for this particular function which has this form. So we want to compute some quantities that will be needed later. First of all, the integral of BE over this edge E is of order h, because B is of order 1 and E is of order, the length of E is of order h. Then we look at the L2 norm of B. Now B is of order 1 and the area of the support of B, which is just two triangles, is of order h squared. So the L2 norm is of order h. For the h1 semi-norm, this is of order h to the power minus 1. So you have to square it, so h to the power minus 2. Then the area of the support is h squared. So that is of order 1. Now we want to have bound on this coefficient lambda e. We know that this is of order h, so put this on the other side, we get h to the power minus 1. And the L1 norm of v, I use Cauchy-Schwarz. Over here, you get the L2 norm of v over the edge e, and you get h to the power minus 1/2. Ultimately, of course, we want to compute the norm of pi v, so that's why we are computing these quantities here. Okay, now we want to compute the norm of v, so over here, we want to have a bound on that norm in terms of h1 norm or L2 norm of v. That means that we need to use trace inequality, and also we need to take into account how the constants in the trace inequality depends on the size of this edge E. So that this would be our triangle E and tau, and you scale it to some triangles, let's say some reference triangle of size 1. We define this function, so let's say v is some arbitrary function. We define this function on the reference element. Then the gradient of that function will scale like this. You will pick up h in front, because basically you are stretching that function. And the L2 norm of that function on the reference element will behave like this, because again stretching, and you will pick up negative power of h because the L2 norm will be increasing. Now the L2 norm on the edge E will behave like this, because it's a one-dimensional thing. The L2 norm over the triangle will behave like this, because it's two-dimensional. Then the L2 norm of the gradient, or the h1 semi-norm, will not change its size. Now by using these scaling properties, let's start with the L2 norm of v on the edge. That we can write as h to the power half times the L2 norm of the reference function on the reference element. At this point we use the trace inequality. Now this would be h1 norm on the reference element. This would be on the reference edge. Then we scale back to the element. h1 norm will split into two pieces, L2 norm and the semi-norm. For the L2 norm, you pick up h to the power minus 1, so you will get h minus half. And for the other one, you just it doesn't change. So the L2 norm on the edge of v is bounded by this quantity. So now we plug that into our bound on lambda. So we have derived this bound already, and by substituting here we simply get h minus 1 power in front of the L2 norm of v over the triangle tau, and just constant independent of h in front of the semi-norm. Now here we only used simple scaling by h, but we know that this argument will actually work when we have a general invertible affine transformation, as long as shape regularity constant is bounded uniformly. Okay, so now we go to evaluating the L2 norm of pi v. So pi v was simply a linear combination of b and linear combination of b's with coefficients lambda e. So we just simply expand that sum here. We get lambda e prime, sum is over e and e prime, and there is L2 inner product between two edge bubble functions. And the edge bubble functions, this L2 inner product will be only non-zero only when e and e prime share a triangle or they are identical. So let's say this relation means either e is equal to e prime or e and e prime share a triangle. So here we simply used Cauchy-Schwarz. Then we can use a simple inequality to bound this product by half the sum of squares. So actually we are grouping in this way. So we take this as one group and take that as another group and apply the inequality to get this. We have this bound because let's say we fix one edge e and see in how many terms of this sum this particular edge e will appear. And this number will be uniformly bounded because this particular edge e will only appear in at most 5 terms. So 4 neighboring edges and in itself. So that's why we have this bound with some constant in front. Now we use the fact that the L2 norm of BE is like h, so the L2 norm squared is like h squared, and then also substitute bound in terms of v on lambda coefficients, and we get this sum over the triangles. So in the end we see that the L2 norm of pi v is bounded by L2 norm of v plus h times the h1 semi-norm of v. So our goal is to show that pi is stable in the h1 norm. So this shows that the L2 part is okay, because on the right hand side we basically have an h1 norm. But it turns out that this pi is not stable in h1 if you compute the h1 norm. So we're going to modify this operator and get Fortin operator that we were after. So in the modification we will need the Scott-Zhang projector. We don't really need to have this particular projector, but we just need the projector that satisfies these bounds. And the Scott-Zhang projector is one that satisfies this. We need this projector sending v to the discrete velocity space that is stable in h1, and also it should have this property on the error. So v minus sv should behave like h times the h1 semi-norm. Then we're going to define our Fortin projector in this way. So Scott-Zhang projector plus a correction, and this correction is done through this pi that we defined before with these edge bubble functions. Then if we compute v minus pi hat v, you can immediately see that this is just I minus pi applied to I minus s times v. And because now we already have this property for I minus pi, we're going to have that property for I minus pi hat. So it satisfies this condition on the Fortin operator. And the only thing we need to show is now to show that this pi hat is h1 stable or bounded in h1. So let's recall the definition of pi hat, and we just now try to bound the h1 norm. Scott-Zhang projector is stable in h1, so we will get h1 norm of v. We write like that, and because this pi applied to that is in a finite element space, so this is in v hat. we can use the inverse inequality. So by inverse inequality, we can bound the H1 norm by an L2 norm if we pay h to the power minus 1. Further, use the estimate or bound on pi. So remember that was L2 norm plus h times h1 semi-norm. So the L2 norm part is here, and h times the semi-norm part is here, and h cancel with that, the inverse power of h. So we write that h1 norm here. Then we use the error bound on the Scott-Zhang projector. We know that this is bounded by, so this is bounded by h times h1 semi-norm of v. So this h will cancel with the inverse power of h, and we will get that. For the third term, we will simply use the boundedness in h1. So that will be, first we get h1 norm of v plus h1 norm of sv, and this is stable in h1. Scott-Zhang projector is in h1. So all these h1 norms will be absorbed into that h1 norm. So we showed that this pi hat is indeed a four-time projector which is stable in h1. So this element p2, p0, which is quadratic for velocity and discontinuous piecewise constants for velocity, this element is Inf-sup stable for the Stokes problem. Now, on this slide, we want to discuss some popular finite elements for the Stokes problem. Here, we have the element that we discussed first, that is P1, P0, which we know that is unstable. And here, this is the element that we just discussed, P2 for velocity and P0 for pressure. Now, if we remember that to show stability of this element, we used a projection onto the edge bubble function space. And there, actually, we only needed, in the beginning, if you remember the condition, we only needed normal component of the difference between V and four-time projection is 0. So that means instead of taking this full quadratic finite elements, we can actually take linear finite elements. Okay, first you take linear finite elements and enrich the space by only adding quadratic edge bubbles which correspond to the vector fields which are normal to the edges. So this saves 3 degrees of freedom, and for the pressure we simply use the piecewise constant. So this element will be actually stable. Now we can also, instead of adding edge bubbles here, what we can do is take the pressure space as P1, which is affine continuous and affine functions for the pressure, and for the velocity you take P1 and add cubic bubble functions on the interior of the elements. So these elements are called mini elements, which have very few degrees of freedom. Because the pressure space for these two spaces, they include piecewise constants, we have local mass conservation. But this mini element, we have P1 for the pressure, so there is no local mass conservation. Similarly to this mini element, what we can also do is we can take P1 for pressure, and for the velocity space, we simply refine the mesh once and take the piecewise affine functions with respect to that refined mesh as the velocity space. So this will also be stable, but there is no local mass conservation, just as this element here. Instead of taking P1 pressure here, we can take also piecewise constant pressure. So if you do that, you will get local mass conservation. Here we see that P1, P0 is unstable, but if we take P2, P1, which means that you have a piecewise affine continuous pressure and continuous and quadratic velocity, we will get a stable element. and these elements are called Taylor-Hood elements. And you have also higher order versions of these elements. This element is in some sense optimal order because we are using one order lower finite elements for the pressure compared to the velocity. For example, for the lowest order element, you're going to get OH squared because you're using piecewise linears for the pressure and piecewise quadratics for the velocity. And in some sense, this element is also optimal because we are not using the full quadratic elements here. So the most this element can do is first order conversions for the velocity. Now, Taylor-Hood elements are because you have continuous pressure space. There is no local mass conservation. If you want to get mass conservation, what you can do is you can actually add piecewise constants simply to the pressure space, and we get elements called modified Taylor-Hood elements, which are also stable. So we get the local mass conservation for that. Now, if you remember, for this element, we had not only local mass conservation, we also had actually divergence-free constraint satisfied exactly. If you want to get that kind of property, you can use the so-called Scott-Vogelius element. These are basically higher order versions of these elements, but the pressure space must be at least order 3, and these elements are known to be stable. They will satisfy exact divergence-free constraint. The mini elements are here. Pressure space is just P1, a continuous P1 space. For the velocity, what we get is, we get first these piecewise affine degrees of freedom on the vertices, then we add one vector degree of freedom in the interior, which is cubic bubble. So B tau is simply the product of those linear functions. Now we write the condition for the Fortuyn projector and do integration by parts just as before. But in this case, because the pressure space is continuous, we will get in some sense the opposite of what we had before. Because in this case, actually the boundary term will vanish and the other term will be non-zero. So imagine we have, let's say, two triangles, right? So this is tau and tau prime. Say for tau, you get normal unit vector going that way. For tau prime, the normal component is going this way, and they will actually cancel each other simply because this is continuous. There is no jump here. So what happens on the boundary? For the boundary, we have V satisfying zero boundary condition, and we need to impose that the Fortuyn projector should satisfy the boundary condition. So this term becomes zero. Now, for the other term here, this is the only potential non-zero term. So in order to make it zero, what we need to do is, similarly to before, we're defining this Fortuyn projector before as linear combination of bubble functions on the edges, but in this case, this is linear combinations on the bubble functions on the triangles. It's simply computing this coefficients lambda so that this actually integral is zero on each triangle, we can ensure stability. The stability proof is very similar to the edge bubble case.